This video covers section 11.5, Exponential and Logarithmic Equations, Objective 3, Solve Equations Involving Exponential Models. One of the exponential models that we want to look at is the half-life. The half-life problems are important applications of exponential models. Now that we have inverse functions, we can determine the time it takes for a substance to decay to a certain percentage of its starting amount. For example, if the half-life of a substance is 1 day, then that means every day that goes by, there'll be a half of what you started with, half a cookie. Now a quarter of a cookie. Night 4 is an 1/8 of a cookie, and then a 16th, and a 32nd, and it keeps going that way. After a short amount of time, there'll be just a crumb of the cookie left over, but theoretically, there is half of a crumb the next day and a half a crumb the following day. We do call that zero at one point in time, but theoretically or mathematically speaking, there still is a substance left over. It could be 0.001% of what you started with. Now let's think about this from another standpoint. If you take a box of cookies and you put that box of cookies in front of about 30 teenage boys, how long do you think it'll take for those cookies to turn into half of the cookies that you placed there in front of them? Meaning, what is the half-life? What do you think the half-life of a box of cookies is in front of a bunch of teenage boys? We know that teenage boys would devour those cookies. We know that there probably would be no cookies left in 1 to 2 seconds. So we would say maybe the half-life of a box of cookies in front of a bunch of teenage boys is around 1 or 2 seconds. Let's just say 2 seconds. They will have devoured those cookies and looking for more. An example that we looked at already in previous videos is caffeine. The half-life of caffeine is known to be 5.8 hours. Suppose that a student drinks or consumes 120 milligrams of caffeine right before class, and let's assume that class is 2 hours and 30 minutes long. We want to know how many milligrams of caffeine will be left after the class is over, after the 2.5 hours go by. The half-life is 5.8 hours. And we started by drinking 120 milligrams of caffeine. The exponential model always goes, whatever you start with, times 1/2 to the t over the half-life, t over 5.8. Makes a lot of sense because if 5.8 hours go by, we would expect there to be 60 milligrams of caffeine. And when you plug in 5.8 into the model, we have 1/2 to the 5.8 over 5.8, which is just 1, or 1/2 to the first power. That's 120 times 1/2, which is half of what we started with, 60. But if we want to know how much is left after the class is over, then we evaluate this function at 2.5 hours. (2.5) divided 5.8. So there's going to be a lot more than 60 milligrams left over because we haven't let a full half-life go by of 5.8 hours. So we'll use our calculator. And we will do 120 multiplied by 1 divided by 2. I'll need to put that in parentheses. Raised to the 2.5 divided by 5.8. We see we have about 89.01 milligrams of caffeine remaining. This function measures the amount that remains. So a little bit has decayed, 120 down to about 90. So about 30 milligrams, 31 milligrams have decayed, which brings us to about 89.01 milligrams left when class is over. So we've been able to do that problem for a while now. What we want to use is the inverse of an exponential function, a logarithm, to figure out how long it will take us to get down to 60 milligrams of caffeine, and then we'll figure out how long it takes us to get down to 20 milligrams. So let's figure out how long it takes us to get down to 60 milligrams of caffeine. The problem is asking us to find T so that the amount remaining A of T is 60. So we have 60 equals 120 times 1/2 to the T over 5.8. Remember, when we solve exponential equations, b to the y equals x, solving for y, we write y equals log base b of x. So we want to isolate this exponential portion by dividing both sides by 120. And now it says 1/2 is equal to 1/2 to the T over 5.8. Now we could say that they have the same base and just equate exponents and say that T over 5.8 is equal to 1. But that's not going to work when we get down to letter C. So we're going to use the log form of this, and remembering that the logarithm is equal to the exponent on my base. My base is 1/2, and my number is 1/2. So that says, if we multiply both sides by 5.8, that says that the time it takes to get down to 60 milligrams is 5.8 times the log base 1/2 of 1/2. And a property of logs state that when the base matches the number inside, you just get 1. So this is no surprise that it takes us 5.8 hours to get to 60 milligrams. So 5.8 hours. To get 60 milligrams left. When will there be 20 milligrams of caffeine? 20 milligrams is not very much. So we started with 120, got down to 20, so we're allowing 100 milligrams to decay. So it's going to take some time to get down to 20 milligrams because it took 5.8 hours to get to 60. Half of 60 is 30. So we've let more than 2 half-life cycles go by. We want to find T so that A of T is 20. 20 equals 120 times 1/2 to the T over 5.8. Isolating the exponential function, we divide both sides by 120 and we get 20 over 120 equals 1/2 to the T over 5.8. 20 over 120 is 1/6 equals 1/2 to the T over 5.8. Now we turn into log form. The exponent, T over 5.8, equals the logarithm. The base is 1/2 and the number is 1/6. Multiplying both sides by 5.8 gives us T equals 5.8 times the log base 1/2 of 1/6. Now for the exam, you'll leave it just like that because I won't allow you to have a calculator. That will be our answer, as we call it, the exact answer. But it's also fun to evaluate this answer. and use the change of base to do that. So we use log of the 1/6 divided by log of the 1/2. So we take 5.8 multiplied by the log of 1 divided by 6 divided by the log of 1 divided by 2. And so it takes 14.99 hours to get down to the 20 milligrams. So around 15 hours to get down to 20 milligrams. And so the validity of that is guaranteed because it takes 5.8 hours to get down to 60, another 5.8 hours to get down to 30, and 5.8 plus 5.8 is 11.6 hours. If you let another 5.8 hours go by, you'd get down to 15, and that would be 17.4 hours. So the 14.99 or 15 hours is right in between the 2 and 3 half-life cycles. So this is used heavily in anesthesia and drugs. They want to tell you when your system will be free enough of a particular drug to allow you to drive your car. And so if the half-life of fentanyl is 3.8 hours, they want to know if you took 750 micrograms of fentanyl, they want to know how long it takes to pretty much leave your system. So here's a practice problem for you to try. I encourage you to press pause in your video and work this out, and come back when you're ready to see the solution. Now that you've had a chance to work this out, I'll work this out with you. We start with 750 micrograms of fentanyl, and we want to know how many micrograms are left over in our system after 2 hours. So we plug in T equals 2 hours. And since we haven't let 3.8 hours go by, we're going to have more than half of 750. We're going to have probably around 400 milligrams left over. So we do 750 times 1 divided by 2 raised to the 2 divided by 3.8. Well, that was a little bit off, but we have 520. 0.74 micrograms of fentanyl still in the system after 2 hours. And when will there be 375 micrograms of fentanyl left? 375 micrograms is the amount. We want to know when the 750 decays down to 375. Isolating the exponential portion, we take 375 and divide by 750. And 375 or 750 is 1/2. Well, since that's a half, we know it only takes us 3.8 hours to get down to a half. Or solving this, we would turn this into log form. The exponent t over 3.8 is equal to log base 1/2 of 1/2. Or t equals 3.8 times log base 1/2 of 1/2. And that says 3.8 hours. But if we want to get down to 250 micrograms of fentanyl, we want to know how long it takes for the 750 to get down to 250. We take 250 and divide by 750, and that equals 1/2 to the t over 3.8. And that gives us 1/3. So we've decayed down to 1/3 of what we started. We turn that into log form. The exponent t over 3.8 is equal to log base 1/2 of 1/3. Multiplying both sides by 3.8. And that would be the answer you'd leave me on a test. Without a calculator, that's as far as we can go. But we can estimate this on our calculator by using the change of base formula. Log of 1/3 times 3.8 divided by log of 1/2. Calculating that on our calculator. .8 times log of 1/3 divided by log of 1/2. And that gives us 6.02 hours. So it takes about 6.02 hours to decay down to 250 micrograms of fentanyl. And so those are the half-life problems. The next application problem that's fun to do is the compound interest formulas. For compound interest. The compound interest formula states that the future value of P dollars invested into an account that pays an annual interest rate R compounded n times per year for T years is given by A is the future value of the principal times 1 plus R over N. R is the rate, N is the number of compoundings raised to N, which is number of compoundings, times the time in years that you let your money work. So if we have an $8,000 investment at an annual interest rate of 0.07 or 7%, compounded monthly, there are 12 months in a year. How long will it take in order for A to equal 15,000? That would be 15,000 equals 8,000, which is P, times 1 plus the rate of 0.07 divided by n, which is monthly, n times t. We have to solve for t. That is an exponential expression. We want to isolate it, so we divide both sides by 8,000. 1, 2, 3. So that's 15/8 equals 1 plus 0.07 divided by 12 raised to the 12t. So that says that 12t is equal to the log whose base is 1 plus 0.07 divided by 12 of 15/8. Dividing both sides by 12, we have this log of 15/8, base of 1 plus 0.07 over 12, all divided by 12. In order to estimate that, we will take log of 15/8 divided by 12 times log of 1 plus 0.07 over 12. So we take log of 15/8 divided by the log of 1 plus 0.07 divided by 12. And I'll put that divided by 12 right next to that. So 9.01 and that's t, so that's measured in years. So it takes about 9.01 years for the 8,000 to grow to 15,000 at 7%. Letter B asks how long it takes for 8,000 to go to 16,000, or how long it takes to double. We want to find t so that our $8,000 grows to 16,000 this time under the same interest rate, same number of compoundings. And this time, we want the 8 to grow to 16, so when we divide by 8,000, we get 2. So this time it's going to say that 12t is equal to the log base 1 plus 0.07 over 12 of 2, or t equals log of 2 base 1 plus 0.07 over 12. To estimate this, we'll have to use the change of base formula. Log of 2 divided by 12, log of 1 plus 0.07 divided by 12. So use the same expression as before. The only change is that we, instead of having 15/8, we have 2. So it takes 9.93 years to double at this rate and this number of compoundings. A lot of investors will use this kind of thing to display their investment strategy to say that their money doubles in around 10 years. So they could invest 100,000 and it'll grow to 200,000 in 10 years. The double life for this problem is around 10 years, so everything doubles in the same amount of time. A dollar doubles to $2 in 10 years, and 2 million doubles to 4 million in 10 years. Practice 7 is for you to try. I encourage you to press pause on your video and work this out, and come back when you're ready to see the solution. Now that you've had a chance to work this out, I'll work this out with you. We want to find how long it takes for this $12,000 that's invested at 8% compounded monthly to grow to $15,000. We need to isolate our exponential portion, so we divide both sides by 12,000. Three goes into 15, 5, and 3 goes into 12, 4 times. This is 1 plus 0.08 divided by 12, all raised to the 12t. Putting that in our log form, the exponent 12t equals the log of base 1.08 divided by 12 of 5/4. We divide both sides by 12. And we have the log of 5/4 base 1 plus 0.08 divided by 12. We'll use our change of base formula to estimate this. Log of 5/4 over 12 times log of 1 plus 0.08 divided by 12. So we're taking this $12,000 and investing at 8% compounded monthly. We've taken 15,000, set it equal to 12,000 times 1 plus 0.08 divided by 12 raised to the 12t. And we're solving for 12t in terms of the log. And now we're going to plug this into the calculator. The expression is very similar to what we had before it, except for now we have the log of 5/4 divided by 12 times the log of 0.08 divided by 12. So this is around 2.8 years. But the 12,000 to 15,000, that's not a very big growth. So that's why it's such a short period of time, 2.8 years. The next problem, we want to figure out how long it takes to double. To 16,000. So we want 16,000 to result after 12,000 is increased at 8% monthly. Sorry, no, we're not doubling this time. So 12 to 16. So we got 16 over 12 equals 1 plus 0.08 divided by 12 raised to the 12t. 16/12 is 4/3. So we write this in log form as 12t equals log base 1 plus 0.08 divided by 12 of 4/3, or t equals log of 4/3 base 1 plus 0.08 divided by 12. All divided by 12. Using the change of base formula, log of 4/3 divided by 12, log of 1 plus 0.08 divided by 12. Pretty similar expression. This time it's log of 4/3 divided by 12 log of 1 plus 0.08 over 12. And so that's around 3.6 years. In these problems, what's always interesting is to figure out how long it takes to double. And we started with 12,000 to get to 24,000. When you double, this is always 2 on this side. So you get 12t equals the log of base 1 plus 0.08 divided by 12 of 2, or t equals log base 1 plus 0.08 divided by 12 of 2 divided by 12. This is log of 2 divided by 12, log of 1 plus 0.08 divided by 12. We've got the same sort of expression, except for this time 4/3 turns into 2. This problem at %, has a double life of around 8.7 years. The problem that we did before was at 7%, had a double life of almost 10 years. You go to 8% compounded monthly, now you have a double life of about 8.7 years. And this concludes the video for section 11.5, Exponential and Logarithmic Equations, Objective 3. Solve equations involving exponential models.